right? I have the recordings from Wednesday. I just have some editing to do on it. And then there was a little network interruption yesterday, so I didn't have a chance to upload it. So I'll upload both Wednesday's class and today's class shortly after we finish today. All right. So any questions on we've done quite a bit. We've in a couple of weeks we reviewed almost the entire course. There are just a couple of things left to do. I'm hoping that you all are able to at least review the material, that you're keeping up, and that you're not only going to rely on what we discuss here, but there's a lot of material that we covered before. You have the slides. You have videos that you could go into and see what parts didn't make sense on needed clarification. And if after all of that, something is still not clear, I'm hoping that you will use the opportunity to ask me and to get it clarified before you have to sit the exam again. And we just out of curiosity, Dr. Radix mentioned something to me too, and I've noticed it here as well, that we have a typical attendance of somewhere between 50 and on a good day, maybe about 75% attendance, but probably closer to about 50%, right? You know, in theory, we supposed to have a 75% attendance rule, and it's not really being enforced, I think, strictly because of online and you know, that they could kind of attend the attendance at kind of attend the class at any time by looking at the recording. But I'm hoping that people would use the opportunity to clarify things that didn't make sense, so that you don't have to, that you don't run into issues when the exam comes around in July or whenever it is that the exam is supposed to be. All right, that's the purpose of us meeting here. So even for her class as well too, if you can't attend all the classes, at least make an effort to be there, to participate, because what I've found, and I mentioned this to you all a long time ago, that if you come to class and just listen, right? If even you're not participating too much or asking too much questions, just the fact that you're listening, sometimes, you know, things it helps you to remember things when you're going back over the course material and so on. All right, so try to attend as many classes as possible. You all have paid for the summer classes, and it is really your opportunity here. And just think of what could happen if you happen to pass and do well. Okay, in many cases. So you know, make use of it. Don't waste the opportunity. Okay, right. So where were we? We ended up last time we did all the thing with the Z transforms and so on. Of course, you have to sit down. There are problem sets and there are past papers to try the questions and see if you get the answers, or if you don't get the answers, and go ahead what do you call it? If something does make sense, and then come back and let me know. If something in the solution is not making sense, then again, come back and let me know as well. All right, so let's go ahead here now. So today's topic has to do with something that was discussed early on in the course, which had to do with piecewise continuous signals. And really the chapter was a chapter on, or a lecture that we were talking about step responses and impulse responses and so on. And the whole thing that in continuous time domain, while we're dealing with a continuous world and the signals, you know, whatever you have coming from sensors and the like, supposed to be continuous. Occasionally you get breaks, right? Transmission breaks, system failures, short circuits. So instead of getting something like this, what may happen is that at some particular point, the signal may disappear here, and then instead it starts back up here, and then it disappears again at some point. So you have this thing going so, and then it disappears, and then it starts back somewhere here, right? Because of a short circuit, because of an open circuit, and so on. So what this is really this part of the course was really trying to sort of get through to people is what happens, what is imposed on a system when these discontinuous signals appear. And we know from before, because we've done, now we have the benefit of hindsight in that we've done the entire course. And we know that when we when we are testing systems, we make use of the impulse response. The impulse response, which leads directly to the transfer function, right? We do the step response, and this is what we saw lets us see if the response for a step is, you know, some kind of thing like this, or if you have behaviors looking like this. The step response basically looks at the transient behavior and oscillations, which is one of the things that we will come to look at before the end. And remember, this step response, if the system has particular types of behavior, and as I said, we've gone through it already, if the system has particular types of behavior like load damping, especially in second order systems, then you tend to get this kind of behavior happening inside of here. So the impulse response gives us a transfer function. The step response gives us transient behaviors and so on. So what happens now if we have a signal, and here's the example here, that we have a signal that is looking like figure Q4A. What happens when a signal like this goes into a system? Now, the particular question is asking us to find the derivative of this, of the signal, which is, okay, that's fair enough. And if you do, when you're doing controls, there are types of control systems that you're going to come across called PID, which is proportional, but this is integral and this is derivative, right? So there are types of control systems that actually take the derivative of a signal or takes the integral of a signal and uses it to make some corrective actions. And you're going to meet that in ECNG 2009. But let's just decompose this thing that we have here, figure Q4A, and just see if I, without answering the question as yet, if I were to impose this on some system that I have. So I have my system here, right? This is the system. I know nothing of it. And this is XT coming in here, right? So XT comes in and XT is increasing from 0. It's a nice linear signal, right? It's increasing from 0 and it's going up to an amplitude here of 1, right? So it's a nice, if you like, this is a 1-to-1 slope, right? So it's increasing 1 unit in time, 1 unit in amplitude for 1 unit in time. That's fine. But all of a sudden now, at this point here, it changes from 1 to 2 units. This now is a sudden change. This is a step change. All right. So if the system was behaving good up to this point, you go here and now at this point in time, we have a step change. So it's a step change. The value is going from 1 to 2. So what does that do? Well, you have now asked the system, basically, you have a normal input coming in and then there's a step input. So what is going to happen now is that you are now looking to see how you're asking the system to respond to a step input. So if the system has oscillations or tends to oscillate in response to a step, then whatever the system is doing, let's say the system was just amplifying. So the 1-to-1 signal that we had here, right? it amplified it. So let's say it's amplifying it by 2. So in the first second, it goes to an amplitude of 2, right? So it has a gain, it's amplifying. But it is a system that has an oscillation or its tendency to oscillate. What is going to happen now is when you put this step response for it, instead of it doing a nice response, and it's supposed to be, this is a 1 volt change here. So what you would expect would have been a 2 volt change, kind of small here. This is the dotted line is what was expected. What may well happen is that the system, if it had a tendency to oscillate, instead of doing this, will do this, right? So where you want a simple answer coming out, or a simple amplification, especially coming out, you're going to get a set of oscillations and so on before it eventually settles down. Now it only has one time unit to settle down. So it may or may not do that, right? And then let's see what happens here again. We're going here, and then at this time now, it changes from 2 back to 1. This is a negative going step. So here we had a positive going step from 1 to 2. Here it's a negative going step from 2 to 1. So this is another step response. And if the system should have just simply gone, and at the end of the time here, come back down to whatever value it was, is going to give me the same oscillation type of behavior again, because I've just hit it with another step. So it's going to give me this kind of thing and then settle down again. And then look what's happening here. We're going here and then another step, another downward step. So this one is going to go from 1 to 0. It is still a unit amplitude step. This is still a unit amplitude step, right? So here you're going to get, you're coming here and it's going to do this kind of thing again, right? Well, actually it's going to go down to 0 here, but will oscillate around the 0 axis, right? That kind of behavior. And then we have a nice negative going, what do you call it? Signal. It is supposed to amplify by 2. There's another 1-to-1, 1 unit 1. So this one may well do what it's supposed to do. But every step change is imposing, every step change now, instead of the system responding to this step nicely, it is doing this kind of behavior. All right? So that is the kind of thing that happens when you impose these, what we call piecewise continuous signals. So they're continuous in a zone here, but here is discontinuous because it's changing value from one point to another. Here is continuous, and then what happens here, right? It has gone down to, this is supposed to be -1. So it's gone down to -1, and then it suddenly goes to 0. So this is a positive going step. So the reporting is going to give us yet another set of transient oscillations on transient. In the transient response, you're going to see oscillations as well, right? That was at the time when we did the lecture, we didn't know enough about the responses yet to understand why. But now we can see that every time you suddenly change a signal because of, it might be accidental. So there's a, as I said, you're in a power plant and there's something, 1 kilometer down the road, some control system has sent a signal. The signal is coming back along the way, along some wires, but there's an interruption because there's a fault in the wires, or one of the connections has been corroded. So the signal comes, but then it disappears for a split second, and then it reappears. So all of that impose sudden sudden changes on the signal, it will suddenly go from one value to another. And any sudden change of a signal from one value to another, the system will interpret that as a step, either a positive going step or a negative going step. Make sense? Yeah?
Yes, sir.
All right? And you have to remember that. So now we know it reinforces what we've been doing all the way through. And now we can see the effect of it and why it is so important. So with that in mind, let's see quickly how to answer the question. Right, so let me clear some of the little stuff out of the way. So the particular question now is asking us now, sketch the derivative of the signal. So this is going in, and the system is supposed to is working a derivative. So it's a derivative controller, and you'll see what that means when you're getting into your controls. But simple now. If I ask you to find the derivative of the signal, because it's piecewise continuous, you have to break the signals up into sections. If you look at it, between -2 and -1, in these spots here, right? Just give me half a second. Right, department matters. Okay, good. So let's break up the signal. The signal has sections, and you take each section at a time. So it is asking you to find the derivative of that. And this you really need to know nothing more than add maths. What is if I give you something, xt, and I ask you to find dx dt, what am I asking you to find? Basically,
the gradient, sir.
Nice, the gradient, right? So you're looking to find the gradient or the slope. So what's the slope of this line here, this section here?
It's 1.
1, exactly, right? Positive. So it says there's 1 unit here, 1 unit here. So the gradient is 1. So if I have to draw the gradient, I'll do it on top of the between here and here, right? Divide dx dt. Let me see if I can remember to put it correctly all the time. So here to here, the gradient is 1. So we draw a line, a constant here. Good. Between -1 and 0, we have a step. Right? So between -1 and 0, let me put this here. For some reason, this didn't copy well. Between -1 and 0, we have a step change. What is the gradient of a step? The gradient here is 0. The gradient here is 0. What is this here? What is the dx dt of a step? This is a gradient or a rate of change. Right? Gradient is also rate of change. So what is the rate of change of a step? It is going from 0 to 1 In how much time? How much time does it take to go from 0 to 1?
Also, it didn't take no time. It went instantaneously.
Right. Instantaneously, right. So where's the slope? 1 over 0 is what?
Infinite. Well, in this, infinite. So,
right. And what do we represent the infinite change as?
well, an impulse.
Nice. Good. So there you go. Right. So that the step change here. At this point in time, we have an impulse. So this is how you draw it. You put an impulse here. Okay. And between here and here, what is the gradient of that? Between -1 and 0, that is a horizontal line, so that has no gradient. Right? Between, at this point now, right at t equal to 0, again, we have a step change, and this is a step going this way. So this is a step, the amplitude is from 2 to 1, so it is a unit step, but it is going negative. So again, it is a sudden change, just like this one here, except that the impulse changes in the negative direction. So that's going to give us a impulse going this way, right? So our negative going impulse here, between here and here, nothing. Here we have yet another impulse. Yet another step change. So here is a step going from 1 to 0. So the rate of change of that is another impulsive change. It's a negative because it's going from 1 to 0. So if you draw it out, the dx dt for this point, again, it's a impulse of height 1, right? And then here now, between 1 and 2, we have, what's the slope of this line? What's the slope of that line?
So that would be -1.
Exactly, right? So -1.
Hello?
Yes,
yeah.
-1, fine. So right here now we have a -1 line. And then at this point now, we have a change going from, this is a step change, and we're going from -1 to 0. So that -1. So that's a positive going step. So at this point in time, we're going to have another positive impulse at this point, okay? Right? So the answer to the problem between -2 and 2 is the green. What we were asking here is the answer is the green sketch here. So we have a slope, an impulse because of this sudden change. Here is 0. We have a sudden change, negative. So there's a negative impulse. We have nothing happening here because it's constant. So the rate of change is nothing. We have a negative going step here again. The rate of change here is negative. And then we have a positive step change here. Okay? Don't put, when you're drawing it, don't put the impulse floating like inside of here. I've seen occasionally, I didn't take out marks for it, but occasionally I've seen people put the impulse like it floating here, right? Don't do that. Okay, the impulse doesn't float. You have to show it's an impulse, it's a unit impulse at this point. So don't put the impulses here, right? I know what they were trying to say, so I was a little bit lenient, but everything happens on the t-axis. So everybody clear with that? Make sense?
Sir.
Mm-hmm.
Just confirming. So how you basically just sizing the impulse based on the gradient?
You size the impulse, yes, based on the step change. So just to, you remember, just for illustrative purposes. So if this, for instance, if this line had done something looking like this, right? So if instead of this, it had done this, right? So it went straight down to 0, right? That would be a step change of 2 units. So it's going from 2 to 0. And I would represent that by an impulse. I would just show here an impulse of 2 units and a negative going impulse of 2 units high. Yeah? Because it had a change of 2 over 0 time. So in theory, just to show it's a sudden impulse, but the impulse, the sort of magnitude of the impulse is a -2. If you like, the weight of the impulse is -2. Yeah?
Yeah. Just one more question.
Mm-hmm.
You said that drawing the impulses, everything happens on the t-axis?
Yeah.
Okay, so regardless of wherever the like, let me say like going like way down or whatever, essentially you would just make sure it's on the t-axis.
Correct.
No floating.
Don't have the impulse floating. It doesn't start at mid amplitude and go. There's a sudden change, and we symbolically represent the impulse as starting on the t-axis, and you draw the height according to the weight of the impulse. Yeah.
Yeah. Thank you, sir.
All right. Nice. Good. Any other questions? Right. And as I said, now you know the importance. When we did it, we didn't have the benefit of having discussed things like system responses and damping and oscillation and so on. But now you can see, after having learned that when you impose a signal like this on a system, that it really forces the system to respond in a very, it's like testing the system with a series of step responses. And if the system wasn't designed to handle that sort of thing, then you're going to run into problems, okay? Right? Okay, so that's, well, the chapter itself, if you go back to chapter 4, was just a general thing that really an impulse, the impulse is derived by its energy. Remember that how we derive the energy or the area, if you like, under an impulse was 1. So it's not so much as saying that delta t is equal to 1 t equal to 0. It wasn't just that. It was really that the energy or the area of the impulse, the weight of the impulse is 1. That was just mathematically to be a little more correct. And we use this now in that chapter to develop this property that we've made use so many times now, which is the sifting property. Okay. All right. So next bit. Right. So this question now, part B, part A just had to do with the signal itself. Part B had to do with stability. And the particular discussions took place in lectures 23 and 24. So we'll have a little look at that and then come back to the problems. This problem actually is a simple block diagram simplification, but making use of the stability issues that we're going to talk about in lecture 23 and 24. All right, so let me just stop this and then stop the share here. And let's see what these lectures were trying to tell us. Uh-oh. Wait a minute, I actually have the recording going on. Okay, have a second, let me stop this. How do I stop my own recording? Okay, I'll have to play it without doing that because I did a recording for you all, but I think the recording is on the slides itself. All right, if you remember when I couldn't attend class that particular day, so I did the recording ahead of time for this one. So let me not view it. You have the recording and you have the videos and the slides available. All right, so one of the things about it is that stability is a big issue in systems, in any kind of thing that you design, whether it's electronics, whether it's telecommunications, energy controls, or whatever. What you want is always that the system, if you have an input, that you get a stable output for whatever you put in. And there are a number of ways that you can determine that, but the main idea about it is that the output is bounded. You have a power supply of some sort to the system. So once you put in an input that is bounded, in other words, within limits, that the output of the system does not go beyond what the power supply can handle, or the system basically doesn't destroy itself. All right? And we also know that when you're doing things like from the Laplace transform, and remember, the Laplace transform itself gives us an insight into system behavior that you would not be able to get just by looking at the differential equation. So if I give you a differential equation of a system, it's not easy to look at the differential equation and figure out, well, you know, if I put as we just spoke about it, if I put a step input onto the system, what is it going to do? You're going to have to plug the step into the differential equation and try to solve the answer, and then see if the answer does what you want. The Laplace transform allows us to model that sort of behavior in the S domain, and from that we're able to see, without solving the equation and without building anything early, that whether the system is behaving or not. And we saw that that certain types of solutions, like this one that I have here, simple poles give you these sort of e to the minus 3t, e to the minus 2t, which are decaying exponents. In other words, as time goes on, they answer, the e to the minus whatever it is gets smaller and smaller and progressively approaches zero as time goes on. So that kind of thing is stable. If you have an e to the plus t, then as the time goes on, you have a growing exponent, and that is the kind of system that will, in the case of electronics, will saturate at the VCC level. But in the case of something like a motor controller, what's going to happen is that you're saying that the motor speed, for argument's sake, will keep increasing until it just can't increase any longer, which is not what you want at all. Right? So from how the transfer function looks, once you can get the answers in the Laplace transform domain, you will be able to see that answers of these sort of forms where you have the poles S plus something, that where the poles are S is equal to, in this case, S equal to -3, -2, and so on. In other words, once the poles have negative real parts, the system is stable. In other words, it drops on into the left-hand half of the S-plane. And you could, again, if you want, you have the transfer function, you could go and plot the poles and see, once the poles are in the left-hand side of the S-plane, then the system is going to be stable. So this particular thing now, suppose we have a system that has a gain, some gain factor, and most controls and most systems that you design have a gain function on it that you can adjust. And a simple thing, I mean, like in electronics, an amplifier has a volume control. Volume is in fact the gain of the amplifier. So if you have an amplifier, for argument's sake, you have to be able to have it in a way where you can increase the volume from nothing to the full output of the amplifier without the amplifier overheating, saturating, blowing the speaker. I don't know if you've ever been in a FET or in some get-together where they have these high-power amplifiers going and they blow the speakers, right? It's not a pleasant thing, especially if you happen to be close to the loudspeaker. It's expensive. You also you risk damaging the amplifier. So you don't want that kind of thing happening, right? That is a kind of unstable behavior. You're overloaded. In that case, not the amplifier, overloaded the speaker, and you took the speaker out. But what happens is that you don't want the amplifier itself to do the same thing. You don't want the amplifier to start to smoke and just blow on you, right? So if you have a model of whatever you're dealing with here, how can I, without having to solve all of the roots and that kind of thing, is there such a way that I could find out whether the system is stable or not, right? And the technique that we use is something called the Routh-Hurwitz stability criterion. And it has to do with being able to see what the poles of a transfer function does without finding the value of the poles. It's easy enough if you only have 2 poles, a quadratic or even 3. You could probably solve that by trial and error. But if you have a system, as most systems do, where you have cascaded systems and each of them is a second order, at the end of the day, you may have something with 5 and 6 poles to handle. And you can't sit down with pen and paper and solve something with 6 poles very easily. So how do I get around that? How can I see what the poles of the system do? And specifically, if the poles happen to be in the left-hand side of the S-plane, which is all I'm interested in, nothing else. So this is where this technique called the Routh-Hurwitz criterion comes in. And it is based on some polynomial theorems that we're not interested in. We right now is just, as I told you in the recording for the class, is that the actual technique itself is just strictly to do with the behavior of the poles in the system. All right. So step 1 on this is to, let me see if there's I can't remember, I think the recording stopped at this point in time, is to find something called the characteristic equation of the transfer function. Whatever the block diagram is, at the end of the day, you get a transfer function that is going to look in its simplest form as some GS over 1 plus GS. This particular bit here, right? The denominator expression, okay? If you set that equal to 0, the 1 plus GH, I'm forgetting the S for the time being, equal to 0, we call this a characteristic equation of the transfer function. And remember, all the poles of the system are here. When you simplify this entire system, all of the poles of the transfer function are located in the denominator. The numerator has the zeros. Zeros are all right because zeros just mean the system shuts down. It doesn't go to its extremes. So we could worry about the zeros afterwards, but the important thing to find out if something is stable is to figure out what the poles themselves are doing. And once you have the characteristic equation, the characteristic equation is a polynomial in S, right? Because we're dealing in the S domain. So this is a polynomial in S, so it's going to look something, this is a typical example here of a 4th order 1. So it could be anything, it could be 3, it could be 5, it could be 6, it could be 2, anything like that. But at the end of the day, when you simplify the 1 plus GH, you're going to get an equation that is a polynomial in S, okay? And if it isn't in descending order, you want to put it in this form. So you you want to get it in descending orders of S. All right? And then what you do, the stability criterion is that you simply tabulate the coefficients as follows. So for instance, if this is a fourth order equation, the first row you put is S to the power 4, N is the highest order here. So this is N minus 1, N minus 2, N minus 3, N minus 4. So you tally it, and the coefficients here, this is AN, this is AN minus 1, AN minus 2, AN minus 3, and AN minus 4, right? So you tally the coefficients according to what we're saying here. So and you draw up a table, and the first row of the table, you put the coefficients for AN, which in this case is 1, AN minus 2, which is 3, and AN minus 4, in this case, which will be 5. And in the S3 row now, right? So if you do S4, you're going to do S cubed next. And then you start with the coefficient of S cubed, right? Which is 2. And then the coefficient, you skip 2 again, and then you go with the coefficient of S, which is 4. So this is the starting point for the tabulation process, right? And then, right? And for completion, you could put a 0 here. It's optional, but any blank is treated as a 0, all right? So the next step now is to do the manipulation that the Sturm, what they call the Sturm theorem. It's a polynomial theorem, right? Sturm, actually the German pronunciation is Sturm, but the theorem now in polynomial theorem, and what we're going to do now is to calculate what we're trying to, we have a row for S4, we have a row for S3. What we're trying to do now is to determine what the row for S squared would look like, what the row for S would look like, S to the power 1 and S to the power 0, right? In this case, we have these two. So we have to tally this one, right? So we use 4 and 3 to give us 2. And then we're going to use 3 and 2 to give us 1. And then we're going to use 2 and 1 to give us 0. Right? So you're going down, and everybody, every row, every row that you want to tabulate, if you tabulate in this row, you need to look at the 2 rows above it. So every row, so the S1, you need to look at the 2 rows above S1, which will be S squared and S cubed, okay? And the manipulation is that to calculate the coefficients for a particular row, like for instance, where we are right now in the in this row here, the next step down to calculate the first value here, we go to the row above, and we're going to take this and multiply it by this, and subtract this, multiplied by this, and divided by the first value here. So it is like when you have a determinant, right? Remember in a determinant, when you are calculating the value of the determinants, how you did it, but we're doing it in the reverse order. In the determinant, you did it AD minus BC, right? In this case, we're doing it the other way around, and we are dividing it by the first term. So you're starting here. So I want to calculate this value here. I'm going to start here. So you put your finger here. So it's this by this, minus this by this, divided by that. All right? And you do that for each of the values. So for this bn minus 1, for this one here now, for this one for here, we're still going to start with the one above, and then we're going to do here minus here divided by an minus 1. So it's always going to start with the first value here. And so you keep going. Right? Bn minus 3, as you say. So you're always going to look at here, and especially keep your finger here. And bn minus 5 would have started with these and then looked at the other one if we had another pair on that side. And so you keep going. All right. The important thing is to use plenty paper. All right. Don't try to complete the table in one shot. You make mistakes. Remember when I was doing the December paper review with you, I made a mistake because I was trying to do it on the screen here. And because of space and not erasing the table on the screen, I ended up using the wrong value. So I put in a value and one of you all pointed it out to me. So what you do is that this is a table that we're trying to complete, but you're doing it in sections. So what you would do, forget the lower part at this point in time. So you would calculate S1 and you do the calculations here. So on your paper, you would have had that this particular value here would have been 2 multiplied by 3 minus 1 multiplied by 4 over 2, right? Which is 6 minus 4 over 2, 6 minus 4 divided by 2, which will give you the 1. And then the other one, 2 by 5 is 10, minus 0 divided by 2 will give me 5. And what you do, you write it over like this now. So after you've done the calculations, we draw the table with S4, well, in this case, S cubed and S squared. And then the next step now is to calculate S to the power 1. You do the calculations, and then you draw over the table now with S to the power 4, 3, 2, and 1. And then you complete it. So the one below here, so S to the power 1, let me just clear the screen a little bit.
Excuse me.
Yes.
But well, trying to figure out why didn't we
I'm not hearing you.
You hear me? Sorry.
Yeah.
Yeah. For the number in the third row, right? Why didn't we find that one for the third column? Under 85 and the 0. Like why we didn't find for that number? What yeah, blank. That space.
Okay. Because if you look at it, at the okay, so this one, we look at these two here, right?
Yeah.
And we got this one. This one, we look at these two.
Right.
Here, we would have had to look at this and something here, but it doesn't have anything around here.
Oh, so it
right?
always has to start with the first one.
Correct. It always has to start with the first one.
Okay.
So
no
this and everybody else here, from the time the table is finished here, so that is why we have nothing here. So you don't even have to put 2, right?
Understood.
Nice. So S1 now, let me just use a different color here. The S1 row now is here. We're going to use the 2. You know, if I'm calculating here, I'm going to use this and this first. So this one is going to be 1 by 4 minus 2 by 5 over 1, which is what?
So -6.
-6, right? And here, I would have to use this and this. But we have a bunch of zeros here. So this one, we're not going to have anything here. We could leave it blank or just put 0. All right? So S1, we complete it. We're supposed to have 6. And here now, we're going to use this row. There are 2 rows above and here. So this is minus 6 by 5, which is minus 30, minus 0, because 0 by 1 is 0, divided by minus 6, so you're just going to get 5. Right? So at that point in time, you have completed the table. You have no more rows to generate here. You reach s to the power 0, which is the endpoint. What the criteria says now is to look at this column here. First off, if you have any negative sign inside of here, the system is unstable. Okay, just give me a second. Excuse me. Right. So you look at the first column, and any negative sign means that the system is unstable. Right? And if the question was to figure out if this particular system was stable, the answer is no, the system isn't stable because we have a negative sign inside of there. Right? So at that point, the technique has answered it first. And what this means is that if this system is not unstable, sorry, not stable, that somewhere in my S-plane, somewhere all of the poles, if they were stable, all the poles were going to be here. Somewhere in this system, we have a pole on the right-hand side, a pole or poles. What you can do is to, luckily enough, this is the technique gives us another little hint in that the number of sign changes, right? The number of sign changes tell us how many poles have, what do you call it? Positive real parts. In other words, how many poles of this system has 4 poles. The number of sign changes in this column is going to tell me how many of those poles going across in the right-hand side of the S-plane. And you determine the sign changes by going down the column. No sign change, no sign change. Here to here is a sign change from positive to negative. So this is one sign change. And here to here is another sign change from negative back to positive. So this is another sign change. So we have, this thing has a total of 2 sign changes, which means that of the 4 poles, 2 of them are located in the right-hand side of the S-plane. Yeah? So as simple as it is, the technique without solving the equation, you are actually able now to see, 1, the system is stable or not. In this case, the system is unstable. And 2, the number of sign changes is actually telling me how many of the poles are on the right-hand side. And if you were to solve this, in fact, and draw, notice that the S-plane here, this is, oops, this is a, let me try and do that a little bit better. Trying to watch a screen and draw on a tablet. Hey, I was supposed to erase that. Okay, let's see if I can erase that. Guess not. Okay. Anyway, so you have come on. Right. So you have the line, and I'm drawing just as crazy as I had before. Can't seem to get it straight. Okay, so that's 0. That's the S-plane line here. Right? And if you look at it now, the 0, 0, this is all of this on this side is right-hand side. So anything across this 0 line, which is here, means that that particular pole, you remember a real part means that you have a e to the plus s, the e to the plus at when you find the inverse Laplace transform. So this part of it is going to give me an increasing exponent in the time domain if I were to solve the equation. All right. So the technique, once you don't make any mistakes, once you use, as I say, calculate the row and write over the table. Calculate a row, write over the table. Right? You have paper inside of here, and it saves you a lot of headache, especially in one of the examples that we were doing. Right? So the other part of it now, that's all well and good. But there's another section now. There are a couple of exceptions. Let me share that now. There are a couple of exceptions, and we'll talk about that. Right? When you're doing the criterion, there are a couple of exceptions that you have to deal with. And the two exceptions are, one, if when you do the calculation, you get a 0 in the first column. Remember, this column is the important one. This is the important column. That's the important column. So if you get a 0 in that column, so the two exceptions, and we'll chat about that next time. The two important things here are, one, if when you tallying, you get a 0 in the first cell of that column. The second thing is if the whole row, right, however big it is, if the entire row are a set of zeros, what do you do? All right, because remember, at the end of the day, once you fill out the table, you have to look and see, you need numbers, especially in this first, well, you need numbers in the first column. So if you have a set of zeros here, it means everything here is going to be 0, and you can't, that's not going to help us out, 0 or blank. So what we're going to look at next time is how to handle those particular situations. And then after that, the general case now, if I have something like a k inside of here, right? If I have something like a k inside of here, it means that somewhere in my table, when I fill it out, instead of only a number, I'm going to get like 2k or 5k plus 4 for argument's sake. I'm going to get these kind of entries inside of here. So what do I do to handle that? This is going to help me determine the values of k to make the system either stable or unstable. Yeah? And we'll be able to answer the particular question, the past paper question at that time. All right. So we have the slides for this. We have the previous recordings for it. So next time we meet, we'll go through it very quickly and then answer the particular question at hand, and I'll take any other concerns or misconceptions that people might have had at that time. All right, so any questions?
So, hello. Well, the question not related to the class. I just wanted to, while I was unable to make Wednesday's class.
Just now, Akim, I'm not hearing you clearly. Yeah, talk.
Okay. Yeah, I was unable to, well, I missed Wednesday's class. I wanted to know if I would have been able to get the record.
Yeah, as I told it. Well. Yeah, I told the class that I have the recordings. I have to upload them. There was a little bit of an internet interruption yesterday, so I wasn't able to do that. Right, okay, so no problem. That class and this class, as soon as I'm finished this morning, I'll upload both sets of recordings for you all to look at. Okay.
Thank you very much.
All right, so let me stop the recording.